Alright guys, so we're going to go through the Unit 1 test review here. So the first question is displayed on the screen, and it says, during takeoff, a plane starts from rest and accelerates at 4 meters per second squared. If it takes 40 seconds to reach the takeoff speed when it leaves the ground, what is the velocity of the plane when it actually leaves the ground? That's the first part, part A. Even though it says S, we'll label it A. Oop, that's not going to work. But that's part A. Here, that'll be better. Yeah. And then part B wants to know how far does the runway need to be to achieve this speed and be able to take off. So again, just going through the process, we would need to draw a picture first. So my quick sketch of an airplane. Put some wheels on the bottom so it can roll. It says it starts at rest and then it accelerates at 4 meters per second squared and takes 40 seconds for it to speed up. So I'm going to just mention rest here because that's an important concept. And then the plane, as it moves, is going to start getting faster and faster, so my arrows are getting larger, and I have it moving to the right in my picture. It doesn't have to move to the right, it's just that's what I drew. So the next step is so we're going to fill out our chart. So in my chart, for horizontal motion, I have the 5 variables for motion. So delta x, which is displacement, vi for the initial velocity, vf for the velocity later on, my acceleration a, and how much time goes by, which is delta t. So if we read through the problem again, it says it starts at rest, so rest means you're stopped. So the initial velocity of the plane is 0. So that's 0 meters per second. Sorry for the writing, I'm using a mouse. The acceleration it tells you is 4, so 4 meters per second squared goes in this box. And then finally, the time it takes for it to speed up is 40 seconds. So we have 3 out of the 5 variables, so we're good to go. So we just need to figure out which equation to select for each part. So for part A, wants to know what's the velocity of the plane at takeoff, so that's going to be the final speed here, so I'll put a question mark. And I want the equation without displacement, or delta x. So that equation is VF, that's supposed to be an F, equals VI plus AT. So when we plug in, we're solving for VF. VI is the initial speed, which is 0. A is 4 meters per second squared. And then 40 seconds is the time. So it's really just multiplying those last 2 numbers together, and you should get 160 meters per second. I have it moving to the right, so it makes sense that it's positive, which it turned out to be in this case. So at the end of this runway, it reaches 160 meters per second, and then it leaves the ground. For part B, we're trying to figure out how far does that runway need to be. So we're actually looking for delta x now. So we can use any equation that we like, as long as we have delta x in it. So I like this one because I feel like it's the easiest one. So delta x equals 1/2 vi plus vf delta t. And we're going to plug into this equation as well. So delta x is what we're solving for. And it's just plugging in 1/2. The initial velocity is still 0, so I can put a 0 in for vi. We just found vf, which is 160. And our time is still the same time period that it speeds up and moves down the runway, which is 40 seconds. So we're going to multiply all those things out. So half of 80, or half of 160 is 80, and 80 times 40 is going to be 3,200 meters. So this is a pretty long runway. If you run 1,600 meters as a mile, this is like 2 miles. So I would expect runways to be pretty big. Probably in reality, the acceleration is a little low for what it actually experiences, but for this theoretical problem, that's it. Okay, so that's number 1. Number 2 is a free fall situation or vertical motion situation. So It says a ball is thrown from the top of a building, so I'm just going to draw the building and the ball. Sort of upward, so it's got an arrow going up. With an unknown initial velocity, so we're not sure about how fast it's moving when it goes up, but it's going to go up, it'll slow down on the way up, it'll reach its highest point, and then it'll start falling down. Sorry if you hear any background noise, the offices are pretty close to each other, so anyway. So if after moving 7 meters below its original position, the ball is moving downward at 25 meters per second, A, what's the ball's initial velocity, B, how much time has passed before the ball moved 7 meters below its original position. So we're looking for how long it takes to get going to that speed after we've thrown it for part B. So again, after we've drawn our picture, which that picture would suffice, we need to figure out kind of our ideas in the problem, so I'm setting up my table to organize them. This time, instead of moving horizontally, we're moving vertically, so it's y direction, VIY, VFY. Instead of having the acceleration as a, we have the acceleration due to gravity on Earth, which is g, and then our time variable again. So we have all those ideas listed in our chart, and now we just have to take these numbers and figure out what things are. So the first number is 7 meters below, so if this is 0, we'll just label that 0 meters. Then it's like down here somewhere, so it's like down here is when we're trying to figure out how fast is it moving. So to do that, again, we're going to have to figure out how far it fell down. So from its original position to where it reaches this point, that's going to be a negative 7 meters. So make sure you put the negative there. If you don't, you'll run into some trouble. The final velocity, it says it's also moving down at 25, so it's going to be negative, and it'll be 25, and that's the velocity at the end of the time period, so that's why it's VF, even though it's not maybe the very end where it's hit the ground, but it's somewhere after when it started. Gravity we know is negative 9.8. So we have 3 out of the 5 meters per second squared. So we have 3 out of the 5 variables again, so we're good to solve. So for part A, we're looking for the ball's initial velocity, so VI. So we're going to put a question mark in for that box, and then we're going to use the equation that doesn't have t. So the equation without t is the squared one, so it's VF squared equals VI squared plus 2g delta y. So plugging into that, VF is going to be negative 25. We're going to square that whole term. VI we're not sure about, but it's still VI and it's squared. Positive plus 2, we're going to use negative 9.8 because we have gravity is directed downward, so that's why we need the negative in there. And then delta y is going to be negative 7 because it is 7 meters below where it originally started, so move down 7 from there to there. Okay, so again, it's just doing algebra and solving. So 25 or negative 25 squared is 625 when you put that in your calculator. VI squared still stays VI squared because that's our variable. 2 times negative 9.8 times negative 7. When I did that, I got 137.2. And then it's from here on out, it's just kind of doing the algebra with this. So we're going to subtract 137.2 from each side. And I'm just going to try to write that quick. So you got VI squared equals the value of 487.8. So 48. Sorry, the mouse is not responding as well as I would hoped. 487.8. And then to get rid of the squared part, we have to take a square root of both sides. So once you finally get to that final part for part A, your value in your calculator should be somewhere close to VI is 22. I got 0.9 here. If you round it a little bit, that's fine. It would be meters per second. It says it's thrown upward, so you would pick the positive root. Remember, for for square root answers, you can choose positive or negative. This one makes sense with positive because it said upward here. So we're going to say it's positive. So that was part A. Part B is just how much time goes by. So part B, we're looking for the time. So this is where I'd put my question mark. And we know all these, so you can pick whatever equation best fits your way of solving it. So VF equals VI plus GT is, I believe, the simplest one for me. Again, signs are very important in this. If you don't put in the positive or negative signs, then you'll get wrong answers. So this is negative 25 for a VF. VI is the answer we just got, so that's a positive 22.09. Gravity is still negative 9.8. And the time variable, delta t, is what we're looking for. So first we're going to subtract the 22.9 from each side. So again, just taking you through the ideas. So this is negative 47.09 is equal to a negative 9.8. Delta t, the 8s I'm having a hard time drawing. There you go. And then you just divide through by negative 9.8 on both sides. So getting that solution worked out and put in the calculator, you will get delta t is equal to 4.805 seconds. So there we go. So that's the answer to question 2, part A and B. All right, guys, so we're at question number 3, which is the one that deals with projectile motion. So it says a drinking fountain projects water at an angle of 50 degrees, so that's in this picture here. And the water reaches a maximum height of 0.15 above the starting point. For this, we're going to try to calculate the speed at which it leaves the fountain, so this overall speed, which I'll just call VI. And then in part B, it wants us to know how much time, or how much time does it take to get to when the velocity is at the smallest point, which would be at the apex, because it's only got the horizontal velocity and no vertical velocity component. And then finally, part C is how far from the starting point has the water moved when it reaches that apex. So we don't know how horizontally how far is this distance here. Okay, so so those are the 3 parts that we're going to try to solve for. Again, just ideas with the projectile motion concepts. We have to separate our motion into horizontal x direction, which is just constant velocity, and the y direction, which is the free fall ideas. So I have the 2 charts set up here. I have the free fall chart, which is delta y and VIY and VFYG delta t, and then I have the horizontal motion, which is constant velocity, so no acceleration in this chart. It's just delta x, VIX, and delta t. Notice also I have VIX and VIY, and their relationship to their angle theta. So VIX is VI cosine theta, and VIY is VI sine theta. So listing out what we know, first off, 50 degrees, that's theta. So we know theta, which will be helpful later on, maybe not right in the beginning. Notice there is no theta in any of these charts here. It's just used with these 2 equations. And then also these equations don't have just VI. So when we're looking for the speed, which is VI, the overall speed, we can't use just one of these equations and get that solution. Like, we have to actually solve for VI in one of these 2. So so that's the first part. It says it reaches its maximum height of 0.15, so that's going to be our apex or our max. So I'm writing apex here, which is the word that I've used in class to describe the highest point. So that's 0.15 meters. At the apex, we should recognize that the speed at the apex in the y direction is 0, so this is going to be a 0 here. And we also know gravity. So that's negative 9.8 meters per second squared. So we know 3 out of the 5, again, we're good. We're looking for the initial velocity VI, so we'll maybe solve for VIY and then use that answer with this equation and solve for VI, which is what I would recommend. So I'm going to work down here so there's a little bit more room, so I'm going to erase this delta x chart because we don't really need it until part C. So coming back to our equations and trying to figure out the right one, we want the equation without t, so that's the squared equation when you're looking at your formula sheet. So VF y squared equals VIY squared plus 2g delta y. So those are the ideas. So VF is going to be 0 because at the highest point it's not moving up or down. VI is what we're looking for, so VIY is the variable. And we know all the other terms in this equation, so 2, negative 9.8 for gravity, and the height that we have is 0.15. All right, so we're going to multiply 2 times negative 9.8 times 0.15, and that turns out to be a negative 2.94. And 0 squared is 0, and we got VIY squared. So now let's just solve them for VIY. So I'm going to take the 2.9 to this side, it becomes positive. So 2.95, I'm sorry, I keep saying 2.95, it's 2.94, excuse me, equals VIY squared. So again, to get rid of the square root, we did this in an earlier problem on this video. We took or to get rid of the square, we take a square root. And when you do that, you get VI y is equal to 1.7 approximately meters per second. If you go another digit, you can, but it's supposed to be around that variable. So that's VIY. Notice that's not VI, so we're going to have to come back here and use that equation, so I'm going to write it in this space. So VIY is equal to VI sine theta. So we're looking for VI. So VIY is that 1.7. VI is what we're looking for. And then sine of the angle, and we know the angle is 50 degrees. So we actually know everything that we need to solve for VI. Sine of 50 is just a number. You can put that in your calculator separately. It's like 0.77, so I'm moving up here now. Follow the arrow. 1.7 equals essentially VI times 0.77 or so. It's not exactly 0.77, but we're just rounding. So to get an estimate, we divide through by 0.77 on both sides. And the initial velocity, which is the hypotenuse of that right triangle, is a larger value. So it should really be 2.2 meters per second is the overall velocity that it is moving at. So that is your answer to part A. So I boxed this one, but I actually had to use that answer up here to get to this solution. So that's part A. For part B, it wants to know, and that's probably the hardest part. Part B wants to know, determine the time when the velocity is at its smallest value. Its smallest value occurs at the apex because it's only the horizontal component. We didn't calculate that horizontal component. We'll need to do that later. But for right now, we don't really need it for part B. So for part B, it says determine the time when the velocity is at its smallest point. So we're going to solve for t out of an equation. So the one that I used for part B was the delta y equals 1/2 VI plus VF times delta t. You can use any of the equations as long as they have t in it. So this one I find to be the simplest most of the time. So 0.15 is the height that's at. A half is still just a half. VIY, and I've left out the little subscripts, that's VIY and VFY. VIY we found to be this 1.7, so make sure you plug in that in this formula. If you plug in 2.2, that's the overall, and that won't be right. Final velocity at the highest point in the y direction is 0, and then t is what we're looking for. So you're going to do half of 1.7, which is like 0.85, so you got 0.15 equals 0.85 delta t, and then you just have to divide through both sides by 0.85. So again, just taking you through the algebra steps here to get to the answer. So the final answer for part B, the time to get to the apex, or the time up, is right here, 0.176 seconds. So it doesn't take very long, almost 0.2 of a second to get to that highest point. So that makes sense too. All right. Last part here, it says how far from the starting point has the water moved horizontally. So that's like the horizontal displacement. So it's looking for delta x. So just listing out the variables that we know. And it's at the apex, so it's the same time here. So we got this time. That's going to be our answer for our use for time in this setup. So Vx and delta t. We're looking for how far it's moved, so that's the displacement aspect. The time here, we're going to put in 0.176. Again, I apologize for misspeaking. And then Vx is the same as Vix because it doesn't accelerate horizontally. So Vx equals Vix, which is Vi cosine theta. And we have Vi and cosine, so Vi was the 2.2 value, that's the overall initial velocity, and we have cosine of 50. Sorry, this mouse is not going the way that I hoped. Let me try to write that a little better. Cosine of that should be a 5, that should be a 0, and degrees. Okay, so that's Vix, and I could make this Vix if you just want to write that little subscript in there and get in the habit. But Vix, Vx, they're the same thing in projectile motion because it does not accelerate horizontally. So that's the x. When you do that, you get Vi is Vix is 1.4 or so. So when you get 1.4 meters per second, that goes in this box. And then we're just looking for delta x. There's only one equation for delta x. So delta x equals Vix delta t. So it's really just multiplying the two numbers that we have next to each other in the chart here. So it's 1.4 times 0.176. And when you do that, you should get something like it traveled 0.25 meters. So it moved like a quarter of a meter stick. And that would be it. So that's the answer to part C of the projectile motion problem on the sheet, that's probably the hardest problem. Okay. So the last part we're getting into is the reviewing of velocity versus time graphs. So for velocity versus time graphs, you look at the graph and it's displaying how the velocity of the object is changing or what the value is as time goes by. So we kind of get a look at this graph and we're going to answer different questions about accelerations and displacements, and then we're going to answer just like what's going on. So actually I think I'm going to go to the what's going on part first because I feel like that's useful in terms of the ideas. If I can just get it to scroll. Okay, so let me shrink it a little bit and answer these questions, because I think if we do that part, that'll help us be better informed when we get answers for the previous part here. So looking at this graph, the different time intervals that we have, it says label each section of the graph where the motion changes. So this would be one set of motion. It looks like for the first 2 seconds. So this is like 0 to 2. So that's one section here. So I'll put like a tick line there. The next time it changes, I'll have it maybe going across that time, full 4.5. So they're basically these time intervals that I listed below, I think, are to the right. I think I have an extra box here. That's okay. I just miscounted when I was setting it up. So 4.5 is the end of this one, and then 4.5 to 7. And then from 7 to 9 looks like it's a certain type of motion, and then it goes 9 to 11, 11 to 12, and then 12 to 15. So those are the time intervals that are going on for the graph displayed here. So hopefully you can see that. And then for each of these sections, we're supposed to describe the velocity value, whether it's positive or negative or 0, the acceleration value, which is basically the slope of the line we're looking at, and then describe the motion of the object, the direction of motion, and how it changes based on the values. So let's just go through the velocities, and that's just simply reading off the graph. So you're just looking at the value, or where the value is, and really we don't have to worry about writing the actual numbers. We'll use those in the calculations, but if we look from 0 to 2 seconds, the velocity is a positive value, because again, this is 0 here, so anything up this way is a positive velocity. Just to remind you, a positive velocity means that it's moving to the right, so it's got a positive velocity, so it's moving right. And let's just start with that part for these sections. So for 2.5 to 4.5, those are all still positive values. So I'm going to put a plus sign there. From 4.5 to 7, those are in the negative, so that's negative. 7 to 9 is a negative value. 9 to 7 has a negative value. 11 to 12, it's at actually 0, so I'm going to write a 0 there. And then from 12 to 15, that last section of the graph, that's going to be a positive value. So again, anything that's positive moves right. So those are the right sections. So when I write the word right, that just means it's moving right. I'm going to drag that down with an arrow. And then these 3 sections here are all lefts. So those are lefts. And then if your velocity is 0, that means you're stopped. So that one's described already completely. We've described what's going on with 11 to 12 because it's just the velocity 0, so it's stopped. All right. So the next part I'm going to look at is the acceleration. So that's the slope of the line. So it's how much it rises or falls. So remember, just kind of reviewing slopes. If it's a horizontal line, the slope's 0. If it's a line that goes up and to the right, that's a positive slope, and down and to the right, that's a negative slope. So again, looking, the first one's 0. Let me change the fonts or the thickness of the line. So that's 0. 2 to 4.5 is a negative slope because it's moving down to the right. 4.5 to 7 is that same slope. It's still going down at that rate. 7 to 9 is back to 0. Then 9 to 11 is positive. 11 to 12 is back at 0. And then 12 to 15, that's a positive slope. So we have the values for the slopes or the accelerations in red there. So now the idea is we need to look at these kind of combinations of velocities and accelerations and determine how the motion is changing. So so we determined the direction of motion, that's what it was, right or left or stopped. And now how it's changing is going to be what I'm going to write kind of to the right of these right, left, stopped ideas. So I'll put a comma. So for 0 to 2, because the acceleration is 0, if your acceleration is 0, that means it's just constant. So anywhere I have a 0 acceleration, it's just constant. So it's just going to move at a constant velocity. So constant velocity from 0 to 2, from 7 to 9. So it's got a constant negative velocity moving to the left from 7 to 9. And then if it's already stopped and it has the acceleration of 0, it's staying stopped. So it's stopped and it's remaining at rest. So it's got a constant velocity of 0. So again, still a constant velocity, even though it's not moving. It's just a constant velocity of 0. All right, so we've answered those with all the zeros, so those are the easier ones. The next part, we got to describe what's happening. So you can look at the graph and describe this, or you can kind of look at the signs of the velocity and acceleration and whether they agree or disagree. So again, if you have agreement, that means the signs are the same. And if they agree, the object's velocity is going to increase. So this symbol here with the velocity arrow going towards the top, that means the velocity is getting bigger. If the symbols or the signs on the velocity and acceleration disagree, they're going to slow down or decrease their velocity, which is the more technical way to express it, but speed up, slow down are generally what people say. The other thing that you can look at is you can think about the speedometer in your car. If you have a dial speedometer, and 0 would be over here on the left side, and you have your dial. If you're at 0, you're stopped. If the line moves away from 0, and this works on the graph as well, if the line's moving away from 0, you'd be speeding up. So you're going from 0 to some number up here. I don't know, I'll write 50. If the line was going the opposite way and the gauge line was moving towards 0, you'd be slowing down. So that's what happens. So there's a couple different ways you can examine these relationships and figure it out. So I'm just going to basically talk through one of them, but I think most people like the does the line move away or towards idea. You can also verify with that, and I probably will do that too. So we've already looked at 0 to 2. From 2 to 4.5, if we look at this part of the line, that part of the line is going towards 0. So I have an arrow just going towards 0. Let me shrink the thickness. So that means if it's going to 0, it's moving to the right because they're positive values. So it's got a positive velocity, but it's slowing down. So I'm just going to, instead of writing slowing, because that's a lot to write and take longer in the video, I'm going to write the velocity arrow is decreasing. Let's look at these two values and see if they agree or disagree. They disagree because you have a positive velocity and a negative acceleration. So disagreement goes along with a decrease in velocity, so that checks out. For the next section, which is still the same slope of the line, which is what messes with people and sometimes they misinterpret it. But if you look at this, we're starting at 0 at 4.5 and the values are getting bigger. Remember, positive and negative, if you have a negative velocity, it just means it's moving left. So we're moving left and our velocity is increasing. So this is a V increase as it moves to the left from 4.5 to 7. Looking at these two signs, we have a negative and a negative. That's agreement. Agreement means the velocity is increasing. I wrote positive there. That was a mistype. So getting back to that idea, so just the velocity is getting bigger, you're increasing the velocity there. All right, so we've covered these two sections. We've already done this horizontal section where it's moving at a constant. The next one, we're starting at 9 and it's going to 11 seconds. So if you check the way the line is headed, it's headed towards the 0. So that would be velocity decreasing. If you look at the signs, you have a negative and a positive. That's disagreement, which goes again with velocity decreasing. The numbers are getting closer to 0. 11 to 12, we are at rest again. And then in the last section here, from 12 to 15, the line is moving away from 0. So moving away from 0 means speeding up. So that's a velocity increase. You can also check to see that the signs agree for the velocity and the acceleration, and they do that. So hopefully that clarifies and reminds you of how to determine what's going on to the object based on the graph. And just be careful whether it's in the positive or negative section, those ideas. So let's go through and kind of, we're going to calculate up here and do the values in the map, or over to the right here. But let's just say what kind of displacement we have and what kind of acceleration you have. So one thing that you should recognize is, like, if you're moving to the right, if you have a positive velocity or a negative velocity, then your velocity and your displacement value always have to agree. So if this is positive, this also has to be positive. So the displacement is positive. So again, these signs in this first column are going to match up with the signs for the displacement. So positive, positive, negative, negative, negative. There is no velocity from 11 to 12. It stops, so there's no displacement. And then from 12 to 15, we're moving to the right. So that's a positive velocity, matches with that. Okay. For the acceleration, that's the slope of the line. So if we look at this slope again, this column and this column are the same. So that's those concepts here. So it would be 0 in the beginning because it's a horizontal line, negative, negative, back down to 0. Then it's positive and 0 and positive. So again, just looking if the line's going up and to the right or down to the right, or if it's horizontal. All right. So so next we're going to get into how to calculate different ideas. So it says calculate the acceleration. I'll do that first in this small section over here. So the acceleration definition, it's the change in velocity divided by the change in time. When we first started looking at these graphs, I explained how to calculate that, and that's just the slope. So if we know how much it rises and falls based on how much time goes by, we can calculate the acceleration of the different sections on the graph. So the first one, it's not rising or falling, so this is 0. For the acceleration values, it's going to be measured in meters per second squared. So the first one, 0 for 0 to 2. 2 to 4.5, it drops 10 in 2.5 seconds. So it'd be down 10 divided by 2.5. So negative 10 divided by 2.5 gets you a negative 4 meters per second squared. And I'm going to stop writing this unit all the time because it slows me down, but it's the same for all these. All right. So from 4.5 to 7, it drops another 10 in 2.5. So it's the same answer. It's still a negative 4. From 7 to 9, it's a horizontal line, so that's 0. 9 to 11, it goes up 10. Whoa, that's really far off. Fix that. So it's starting at negative 10 and it goes to 0, so that'd be a gain of 10, so that's plus 10. And it takes 2 seconds for that to occur, because from 9 to 11 seconds is 2. So positive 10 divided by 2 is a positive 5 meters per second squared for that one. 11 to 12 is still 0 because it's a horizontal line section. And then in the last part, from 12 to 15, it goes up to 12. This value here is at 12. And then it takes 3 seconds, so it would be 12 divided by 3, which is a positive 4. So gaining 12 divided by 3 is positive 4. So those are the accelerations for this graph. And now the next part is going to be able to calculate the displacement. So there's a couple ways you can do this. You can say the displacement is just the area between the curve and the time axis. So we did that where we like shaded in and colored in the different sections of the graph, so I could like figure out, okay, what shape is this, and figure out the area of that shape, or the next shape. I feel like that way might be harder for some students, so I usually just use the formula. So the other way to do it, and either way works, so do which works best for you, that you understand. We started with the areas, but then we started to get these equations, and using the equations that we have, you have 1/2, you can read the velocity information directly off the graph, so you can get VI and VF off the graph, and then the time period that it lasts for as well. So we already know the answer should be positive or negative. We already did these as well. So the first one was 0, negative, negative, then another 0, then a positive, then a 0, and then another positive. So like you can make sure that your ideas match up with the calculations we're doing. So I'm going to use this formula a lot. From 0 to 2 seconds is the first section. So this equation works with any section or any shape. The areas sometimes can be a little more complicated, like this is a rectangle, that's a triangle, another triangle, a rectangle. So these are all pretty simple. If you have kind of a trapezoid shape, then that's harder, but you just have to add a triangle and a rectangle together. So for 0 to 2 seconds, it would be delta x equals 1/2. The initial velocity is 10. The final velocity is 10, and it's for 2 seconds. So half of 2 is just 1. 1 times the quantity of 10 plus 10 is just going to get you 20, and it's a positive 20. All right, so it's a positive displacement, because it's got a positive velocity, it's above the horizontal time axis, so that's a positive value. From 2 to 4.5 is the next one. And again, delta x equals, you just have to read the values, 1/2. The initial velocity at 2 seconds is 10. The final velocity at 4.5 is 0. And this is 2.5 seconds. So when you multiply half times 2.5, you get 1.25, and then you multiply by 10, that's going to get you 12.5. Again, use your calculator. There's no reason to try to do this in your head. I just am sitting here and talking through it. I've already worked out all my answers on my paper, so that's where I got 12.5. Then we have 4.5 to 7 seconds is the next one. So again, same formula, delta x equals 1/2. The initial velocity is the starting velocity is at 0 at 4.5 seconds. The final velocity at the end is -10, and this is where that negative is very important because it's moving left at 10. And then it's 2.5 for the time period, because from 4.5 to 7 is 2.5. This gets you the same amount, but it's a -12.5 this time. So you're moving left 12.5 meters. So just remember your negative signs. From 7 to 9, pretty simple. You got same equation, delta x equals 1/2. Initial velocity is -10. Again, remember the signs. That's supposed to be a 10, not a 6, even though it looks like a 6. Final velocity is -10, and the time is 2 seconds. So this is going to be a -20 meters. So that's the 7 to 9 section. 9 to 11 is going up back towards the 0 axis. It's for 2 seconds, and it'd be delta x equals 1/2. Initial velocity is the -10. The final velocity after 2 seconds, when I get to 11 here, I read off it's at 0. And again, it's 2 seconds. So, so this one's just a -10 meters. Again, that's a 10, not a 0. 11 to 12, you don't have to be calculating anything. It's stopped because the velocity is 0. If you're stopped, your displacement is 0. So you could plug in, it'd be 1/2 times 0 plus 0 times 1. It's not really an important thing to show. You can just recognize, oh yeah, that's that variable, or that value of 0, because you're stopped, you're not moving. And then from 12 to 15 seconds, last one, delta x equals 1/2. The initial velocity it's starting at is 0. It's reaching a positive 12 meters per second, and it takes 3 seconds for that to occur. So if you do half of 12, that's 6. 6 times 3 is going to be a positive 18. So positive 18 meters is the final area or displacement for this graph. Okay, so sorry this is a long video, but I wanted to make sure I showed you everything and talked about it in detail. So hopefully that'll help you prep for the review and for the test. Good luck and have a good one.